Welcome to the deep dive, where we analyze the cutting edge of research to extract the signal through the noise. Today, we are undertaking a deep dive into an idea that, well, it fundamentally challenges the resource allocation philosophy across the large language model industry, specifically regarding complex reasoning. It's called the less is more reasoning, or LIMO hypothesis.
That's right. It's a really fascinating piece of work.
For years, the path to mastering intricate, multi-step logical deduction, the kind required for advanced mathematics or competitive programming, it's been dominated by the supervised fine-tuning paradigm. And this conventional wisdom, it basically insisted you needed massive brute force scale data sets featuring hundreds of thousands, sometimes even millions of examples. The core assumption was that reasoning was somehow an emergent property of just data volume.
Yeah, the more is more philosophy.
Exactly. But this LIMO paper, it just flips that script entirely. It comes out with a really provocative result. The LIMO model achieved superior performance on competition-level math benchmarks, including the highly challenging American Invitational Mathematics Examination, AM.
Right.
And it did this using an astonishingly minimal training budget. Just 800 highly curated samples. 800.
The efficiency figures here are really what demand attention. The paper reports obtaining an 874% gain on the AIME-24 benchmark, measured via pass at 1 accuracy.
Which is just huge.
It's massive.
Yeah.
And crucially, this was done while utilizing only 1% of the training data typically required by prior state-of-the-art fine-tuned models.
Yeah.
So, this isn't marginal optimization we're talking about. This is a radical revision of the data efficiency curve for deep reasoning tasks.
Yeah, it's not just tweaking things at the edges.
Not at all. And what's critical for our expert audience to understand is that the LIMO team isn't claiming they just, found some magic C data set by luck. They're rigorously validating a core conceptual shift they formalize as the LIMO hypothesis.
Okay.
And this hypothesis states that sophisticated reasoning capabilities are elicited, not really acquired post hoc after pre-training. And this elicitation depends on the synergy of two independent but essential factors.
Right, and those factors are really the pillars of our entire discussion today, aren't they? Factor one is the sheer completeness of the model's pre-trained knowledge base, essentially. The foundational mathematical and coded knowledge that's already latent within the vast parameter space. This is the model's inherent ability to know.
Exactly. It's what the model already contains from its initial training. Factor two is the effectiveness of minimal strategically designed demonstrations. They call these cognitive templates.
Cognitive templates, okay.
Yeah, and these templates, they don't teach the model new facts. They instruct the model on the process of extended problem solving. They guide it through something that looks a lot like human deliberation, self-correction, structured thinking.
So it's about teaching the how, not the what.
Precisely. The LIMO hypothesis argues that if a foundation model is rich enough, factor I is strong, then you only need to teach it the mechanism, the process factor two, with a minimal amount of really high-quality data.
Got it. So our mission today is to unpack this efficiency revolution. We'll first establish the intellectual context that kind of enabled this shift away from just pure data scale. Then we'll dedicate significant time to detailing the multi-stage data curation process, explaining exactly how they got those critical 800 samples. We have to get into the weeds there.
Absolutely. The curation is key.
Then we'll review the main experimental results, especially that head-to-head comparison against data-hungry models, which is pretty stark.
Yeah, that's where it gets really compelling.
And finally, we'll delve extensively into the ablation studies. These are what rigorously test and validate every specific component of the LIMO hypothesis.
Right. Breaking down why it works.
Yeah.
Okay, so let's start with the historical context. The prevailing paradigm, particularly until quite recently, was really rooted in this assumption that reasoning required massive supervised fine-tuning.
Right, the SFT approach.
Exactly. The thinking was you had to cover this immense space of logical operations and problem types. Researchers felt, essentially, that they had to demonstrate every possible logical path, which naturally led to training on tens or even hundreds of thousands of examples.
Just trying to cover all bases.
Yeah, and this was driven by the inherent complexity of these tasks, right? Tasks demanding multi-step logical deduction and, crucially, verifiable, structured solution paths.
And the problem with that massive data volume approach wasn't it always the question of, quality versus quantity? When you scale SFT to those levels, are you truly driving generalization, or are you just over-optimizing for superficial memorization? Getting good at the test, basically.
Precisely. That was the big concern. And findings by several research groups, particularly those studying model robustness, consistently highlighted issues here. Models trained on these huge SFT datasets, they often exhibited significant performance variance.
Meaning they were brittle.
Very brittle. Or sometimes they'd outright fail when numerical values or symbolic representations within a question were subtly altered, even if the underlying logical structure remained identical.
Ah, so changing a 5 to a 6 could break the reasoning chain.
Potentially, yes. If the model had truly generalized the reasoning process, these minor alterations shouldn't cause a collapse, but they often did. This raised serious doubts about whether SFT was actually teaching reasoning or just refining knowledge retrieval based on highly similar training prompts.
So it was more pattern matching than actual deduction.
That was the suspicion. The LIMO paper directly addresses this computational and, frankly, conceptual inefficiency.
And they argue that this whole data-intensive paradigm, it's unnecessary now because of fundamental shifts in the LLM ecosystem over the last few years.
Exactly. They point to two main revolutions. The first is what they call the knowledge foundation revolution.
Okay.
This is crucial. Today's foundation models are just fundamentally different from the models of, say, 3 years ago. Through vastly scaled pre-training, these models ingest unprecedented volumes of high-quality mathematical, scientific, and code content.
You see that in the reported token counts for pre-training, right?
Absolutely. Look at the published data, the progression from something like Llama 2's 1.8 trillion tokens to Llama 3's much larger context, which deliberately focused 3.7 trillion tokens specifically on mathematical reasoning and associated code generation. That's a massive increase in relevant pre-training data.
So the implication is that contemporary high-quality LLMs already possess this rich, latent mathematical knowledge.
That's the core idea. The knowledge is likely already there, embedded deep within the model's weights.
So the challenge shifts entirely then. It's no longer about knowledge acquisition like training the model to know the rules of calculus or geometry from scratch during fine-tuning.
Right.
It becomes knowledge elicitation. It's about creating the right cognitive trigger, the right prompt or demonstration to get the model to perform the complex, multi-step deliberation needed to solve a novel, challenging problem using the knowledge it already has.
You've nailed it. And the second enabler they highlight is the inference time computation scaling revolution.
Right. This is about giving the model more thinking time.
Sort of, yes.
Yeah.
More accurately, we're now exponentially better at providing the LLM with a significant cognitive workspace during inference. This is where techniques that scale longer reasoning chains come into play.
Like chain of thought, but more advanced versions.
Exactly. Things like parallel sampling, symbolic tree search, and even models trained via reinforcement learning, specifically to generate lengthy chains of thought, or COT, that go far beyond just simple next token prediction.
And these aren't just longer, they're qualitatively different, right?
Absolutely. What defines these modern effective reasoning chains is often the inclusion of human-like meta-reasoning components. Things like explicit self-reflection steps within the chain, verification steps where the model checks its own work, and even backtracking to correct initial errors if it finds them.
So the model can kind of think out loud and correct itself.
That's a good way to put it. These extended computational reasoning chains allow the model to apply its rich, pre-trained knowledge base iteratively and more robustly.
Okay, so putting it all together.
Therefore, the LIMO hypothesis is essentially a formal recognition of these two revolutions happening in parallel. If the model is sufficiently knowledgeable, that's factor I, thanks to better pre-training, and it possesses the mechanisms for extended deliberation, thanks to inference time scaling, then the only missing piece is a minimal, high-quality set of instructions. Those are the cognitive templates.
The triggers.
The triggers, exactly,
Ah.
to activate that latent capability. Formalizing this LIMO elicitation threshold means defining exactly how minimal and how effective those exemplars, those demonstrations, need to be to show the model these extended deliberation and structured problem-solving processes.
It's a fundamental shift from teaching subject matter during SFT to teaching meta-reasoning.
Teaching it how to think based on what it already knows.
Precisely.
So the LIMO methodology sounds like it's basically an engineering solution designed to prove the LIMO hypothesis. If quantity degrades performance, as that Newman math example suggested,
Right, where more data made it worse.
then quality must be the absolute priority. And you mentioned this focus is directly inspired by LIMO-less, is more for alignment, but applied here specifically to complex reasoning tasks.
That's the connection they draw, yes. Extending that less is more ideology.
So the goal was to distill complex, competitive reasoning instruction into just 800 compact yet potent samples. That's the target. Exactly. And the foundational task for that was establishing a candidate pool of problems that was comprehensive in scope, but also inherently challenging. They didn't just grab a general math corpus off the shelf.
No random grab bag of math problems.
Definitely not. They meticulously assembled problems from data sets recognized for their rigor. This included things like Numina Deepscaler, which is known for its structured problem-answer pairs, historical AIM exams, a key source of difficulty, the broad math dataset, and several demanding Chinese national examination papers, like the high school Gaokao and the university entrance Kaian exams.
So a very diverse but high difficulty starting point.
Yes, and this initial massive pool contained literally millions of problems.
But okay, the challenge isn't having millions of problems. It's finding the 800 most useful ones. How did they possibly ensure that the selected problems were genuinely challenging enough to elicit that multi-step deliberation process we talked about? How did they avoid problems solvable through simple recall or shallow heuristics?
Yeah, that's the critical filtering step. It required a rigorous, systematic, two-step filtering process. They actually visualize this quite well in the paper. You can think of it as stress testing the candidate problems using increasingly strong LLM reasoners to isolate only the toughest cases.
Okay, step one.
The first step was coarse difficulty filtering. They used a relatively capable but specifically short chain of thought model, Qwen 2.5 Math 7b Instruct, as the initial discriminator. Think of it as their B-team model for difficulty screening.
So not the strongest model, but decent.
Right. Any problem solved correctly by this model within just 4 attempts was immediately flagged as too trivial and excluded from the pool. This very efficiently filtered out the vast majority of easy and medium difficulty problems, which allowed them to save computational resources for the finer analysis later.
Okay, prune the easy stuff first.
Cool.
Smart. Then they focused their heavy computational resources on the problems that actually stumped this B-team model, which leads to the fine-grained difficulty assessment.
Exactly. Now they brought in the heavy artillery, DeepSeek R1, distilled Qwen 32b. This is a significantly stronger reasoning model, known for its multi-turn reasoning capabilities, a real A-team player.
Okay.
For every single problem that survived the first filter, they sampled a substantial number of potential solutions, 32 solutions per problem. The empirical success rate across these 32 high-powered attempts served as the true difficulty metric.
So they're really hammering each problem with a strong model.
Absolutely. And here's the core filtering mechanism. They retained only the most challenging problems, specifically those problems that were successfully solved in only 1 to 3 attempts out of those 32 samples generated by the strong model.
Wow, so even the top-tier model struggled significantly with these.
Precisely. If a top-tier model struggled that much, it meant the problem almost certainly required maximal effort and extended non-trivial deliberation. It wasn't solvable with a simple trick. This aggressive, precision-based filtering yielded the high-challenge LIMO pool of just 2,125 problems.
Down from millions to just over 2,000 really hard problems.
Correct. And a critical methodological note here, especially given our expert audience. To ensure the fidelity of out-of-distribution generalization wasn't compromised.
Making sure it wasn't just memorizing answers that might appear in the test sets.
Exactly that. They performed thorough N-gram deduplication against all the standard evaluation benchmarks they plan to use later. This guarantees, as much as possible, that the models fine-tuned on LIMO were learning to reason, not just memorizing solutions that happen to overlap with evaluation questions. It protects the O generalization claim.
Okay, that's crucial for validating the results.
Yeah.
So now they have these 2,125 high difficulty questions. The focus must shift from question quality to reasoning chain quality. That's factor 2 of the hypothesis, right? The cognitive template.
You got it. So solutions for these problems were generated using multiple state-of-the-art models, like DeepSeek R1 and QWQ32b, to ensure they got a diversity of high-level reasoning styles and approaches. Right. Then, the researchers systematically analyzed these generated solutions to define the 4 key characteristics that constitute a high-quality elicitory reasoning chain. This is really the heart of defining that cognitive template.
Okay, let's break down those 4 characteristics. They seem really important for understanding what LIMO considers good instruction.
Definitely. First, elaborated reasoning. This was quantified primarily by the length of the solution and was assigned a hefty 30% weight in their scoring system.
Longer is better.
Essentially, yes, within reason. This metric prioritizes comprehensive, step-by-step exploration of the logical path, It discourages collapsed or overly concise answers that might hide the actual reasoning steps.
Okay, that makes intuitive sense. Longer, detailed steps demonstrate the internal process better. But the next one, self-verification, with a 20% weight, that's fascinating. It measured the frequency of validation-related words, things like check, verify, or re-examine.
Yes. This is basically the model grading its own work or showing its work-checking process in real time within the reasoning chain. By weighting solutions that explicitly include these self-correction or consistency checks, the SFT process deliberately teaches the model not just to find the answer, but also this vital meta skill of self-monitoring during problem solving.
So it's building robustness into the reasoning process itself.
Exactly. It's a deliberate design choice aimed squarely at enhancing the model's reliability during complex inference, especially on problems where it might initially go down a wrong path.
Okay, third characteristic, exploratory approach with 25% weight. This measured the presence of tentative expressions, words like perhaps, might, or let's consider. Now, why prioritize tentative language in a reasoning chain? Doesn't that sound like a sign of weakness or uncertainty?
You might think so initially, but actually, for truly complex problems, this signifies robustness. It captures the human process of considering multiple possibilities or sub-hypotheses before committing to a final conclusion or path.
Ah, so it reflects a more thorough search process.
Precisely. By weighting these exploratory phrases, the curriculum encourages the model to generate broader search spaces internally during inference, increasing the likelihood of finding a non-obvious solution path. It's essentially rewarding deep consideration over premature, linear certainty.
That's a really interesting insight into complex problem solving. Okay, and the final one, adaptive granularity, also 25% weight. This tracked the use of connective phrases like therefore, since, and consequently. I assume this is about ensuring a structured, logical flow.
You got it. It ensures the solution doesn't just list a bunch of steps, but explicitly signals the logical connection between those steps. It guarantees that the reasoning chain is not just a sequence of calculations, but a demonstrable, traceable, logical deduction.
Making the reasoning explicit.
Exactly. And they were careful to normalize all these keyword frequencies by the text length to prevent longer solutions from unfairly getting higher scores just by virtue of being longer.
Right, fair normalization. So, using this meticulous rule-based system, they assign a quantifiable quality score to every generated solution in that 2,125 problem pool.
Correct. And the top 800 quotient solution pairs those boasting the optimal combination of the most challenging questions and the highest quality reasoning chains according to the scoring system that formed the final LIMO dataset.
Wow. Okay. That entire process, from the initial millions down to filtering by difficulty, then generating solutions, and finally scoring those solutions for reasoning quality to get the top 800, that really is the engineering embodiment of the LIMO philosophy, isn't it?
It absolutely is. It's all about maximizing the instructional quality per sample.
Right. So before we dive into the results themselves, let's just quickly confirm the technical implementation details for the audience. The team used supervised fine-tuning, SFT, on the Qwen 2.532B instruct backbone model. And that model was chosen specifically for its strong math pre-training, right? Addressing factor I, the hypothesis.
Exactly. It had that enhanced mathematical and code foundation they needed. They trained it for 15 epochs using full parameter tuning, not Lorai or anything lightweight optimized with deep speed 03.
Which you'd need for a model this size with long context.
For sure. And critically, the maximum sequence length was set quite high at 16,384 tokens. This provided ample space for those high-quality, elaborated chain-of-thought solutions that the LIMO dataset prioritized.
Okay, setup confirmed. So looking at the in-domain performance highlights, the efficiency gains they got with just those 800 samples are, well, statistically they seem irrefutable. LIMO achieved 63.3% accuracy on A24.
Which, remember, is the gold standard for competition-level math assessment. It's notoriously difficult.
Right, and to put that 63.3% in context, it significantly outperforms strong proprietary models like OpenAI's O1 preview, which reportedly scored 44.6% around that time, and even the strong QWQ32B preview baseline, which was at 50.0%.
So it wasn't just a competitive result using less data. It was actually a leading result, achieved on a tiny fraction of the typical data budget.
That's the kicker.
And the comparison to LIMO's other scores, like 95.6% on Math 500 and 96.3% on AMC 23, confirms that this instruction set wasn't just tuned for aim. It was broad enough to handle a range of difficulties effectively.
But the real punch, I think, comes when we look at that direct apples-to-apples comparison of quality versus quantity.
Yeah.
This is maybe the most damning indictment of the old more data is always better paradigm.
I agree. This is where I really want to pause and analyze the finding carefully. The researchers took the exact same LLM backbone, Qwen 2.532b instruct, so no architectural advantage, and they fine-tuned it on massive external math data sets. Then they compared the average performance across 10 different benchmarks against their model trained on just the 800 LIMO samples.
And the large data sets they used for comparison were Numinomath 100K with 100,000 samples.
125 times larger than LIMO 800.
And OpenThought's 114K with 114,000 samples.
So
And the results were, frankly, shocking. Numinomath 100K, despite being 125 times larger, achieved only 32.3% average performance across these benchmarks. OpenThought's 114K, which is generally considered better curated, still only managed 58.3% average performance.
and LIMO 800?
LIMO 800, meanwhile, dominated with 78.1% average performance.
That gap is enormous. But the performance degradation seen with Numinomath 100K is the truly central finding here, I think. The base Qwen 2.522b instruct model, before any fine-tuning at all, achieved 49.9% average performance on these benchmarks.
Okay, so the starting point was about 50%.
Right. Numinomath 100K, despite adding 100,000 examples presumably intended to teach math reasoning, actively drove performance down from 49.9% to 32.3%.
Wait, hang on. Using 100,000 times the data actually degraded the performance significantly below its original capabilities?
Yeah.
How is that even possible? Does this imply that low-quality data acts as a form of catastrophic unlearning? Like it overwrites the good reasoning templates the model already possessed from pre-training?
That's exactly the implication the authors draw, and it's a powerful one. The hypothesis is that the lower quality data in Numinomath 100K, likely featuring inconsistent, maybe erroneous, or overly simplistic reasoning chains, perhaps lacking those crucial self-verification or exploratory components we discussed, effectively poisons the cognitive instruction set.
It teaches the model bad habits.
Essentially, yes. Instead of eliciting the latent, robust reasoning capabilities established during pre-training, the model is retrained or biased towards these inferior, potentially noise-filled reasoning patterns present in the massive dataset. It forces the model to learn a less effective, less reliable reasoning strategy.
Wow.
This forcefully underscores that strategic curation isn't just an efficiency gain. It might actually be a necessary safeguard against performance corruption when fine-tuning for complex tasks.
That completely shifts the narrative, doesn't it? From more data is generally better to bad data is actively harmful for reasoning. It really redefines the role of the data scientist or ML engineer in SFT from just being a data collector to being a crucial quality gatekeeper.
Absolutely. Quality over quantity becomes paramount, not just desirable.
Okay, so beyond these striking in-domain results and the quality versus quantity comparison, did LIMO also show good out-of-domain generalization? That's key to proving it wasn't just overfitting to those 800 samples.
Yes, it did, and this is crucial. It confirms the fine-tuning didn't just result in memorization. It seems to have instantiated genuinely generalized reasoning skills. On diverse math challenges like Olympiad Bench, which contains problems different in style from the training set, LIMO achieved a strong 67.6% accuracy.
Okay, that's promising.
Even more indicative of true generalization, perhaps, was the performance on novel cross-lingual exams. They tested it on those rigorous Chinese high school and university entrance exams, CH Math, Gaokao, Kaiyan, which have different stylistic conventions and problem types. LIMO showed massive gains there, too. For instance, it achieved 84.2% on CH Math, compared to a strong baseline like QWQ32B Preview's 68.5%.
So it transferred well across different mathematical traditions?
It appears so. Furthermore, the transfer of the underlying reasoning skills beyond pure math was confirmed by LIMO achieving a solid 70.7% accuracy on the multidisciplinary GPQA benchmark. This benchmark includes complex questions from physics, chemistry, and biology that require logical deduction.
So the mathematical cognitive template it learned seems to generalize, at least to some extent, to complex logical deduction tasks across different scientific knowledge domains.
That's the implication, yes. It suggests the fine-tuning enhanced a core reasoning capability, not just math-specific pattern matching.
Okay, so the primary results establish the proof of concept. Minimal data can lead to superior results, but the extensive analysis and the ablation studies are really what solidified the LIMO hypothesis scientifically, right? They systematically tested each variable to figure out which specific components are driving this incredible efficiency.
Exactly. This is where they really drill down. Let's transition into analyzing the specific research questions, the RQs, that they used to test each pillar of the hypothesis, starting with the impact of the quality of the instructions themselves, the reasoning chains.
Okay, RQ1. This aimed to isolate the influence of the reasoning chain quality, specifically making it independent of the question's difficulty. The methodology, as I understand it, involved selecting 500 fixed questions from the LIMO dataset.
Right, the same questions for all test conditions.
But for each question, the team possessed multiple correct solutions that they had already categorized into 5 distinct quality levels,
Right.
L1 through L5, based on that rule-based scoring system we discussed earlier, L5 being the highest quality chains.
Correct. So they trained separate models using only solutions from each quality tier.
And the results.
The results, which they summarize nicely in Figure 3 of the paper, illustrate an almost perfect correlation between the instruction quality and the resulting model performance. Models trained exclusively on the highest quality L5 solutions achieved substantially and consistently higher results compared to those trained on the lowest quality L1 solutions. This held true across both the challenging AME24 benchmark and the broader Math 500 benchmark.
So it wasn't just about getting the final answer right in the training data.
Not at all. For our expert listeners, this isn't just saying better data is better. It demonstrates quite clearly that the structure, the self-verification steps, the exploratory language, the logical flow of the demonstration itself fundamentally dictates the resulting efficacy of the fine-tuned model. The cognitive template works exactly as intended by its design principles, and this effect is independent of the specific problem set difficulty, since the questions were held constant.
Okay, so that validates factor 2, the quality of the instruction in isolation. The way you demonstrate the reasoning matters immensely.
Wow.
All right, so if the quality of the instruction, the reasoning chain, is paramount, what about the difficulty of the subject matter used for training? RQ2 investigated how the problem difficulty itself enhances generalized reasoning.
Yeah, this tackles the other side of the data curation coin.
So they designed 3 distinct training sets, each with 500 problems. Importantly, all were fine-tuned using only high-quality solutions, L5 quality presumably, but the problems themselves varied in complexity. They had simple 500 using lower-level math problems, levels 1 to 2,
The easier stuff.
complex 500, mid-level math problems, levels 3 to 5, and advanced 500, using only AIM competition-level problems. So, a clear difficulty gradient in the training questions.
Exactly, a controlled experiment on question difficulty.
And the results here.
The results showed that simply focusing the training on higher difficulty material yields massive returns, especially for tackling hard problems later. Just modifying the problem selection from the simple 500 set to the advanced 500 set led to a 16% absolute accuracy improvement on the AAM 2024 evaluation benchmark. The advanced 500 trained model reached 51.5% on AIM.
That's a significant bump, achieved solely by optimizing the input difficulty, holding everything else constant, same number of samples, same quality solutions, same backbone model.
Correct. But what's most critical here, I think, is the generalization effect they observed. The model was fine-tuned only on the highly difficult advanced 500 set, the AIM problems.
Which you might worry would make it overly specialized.
Right, you might think it would struggle with easier stuff. But it still achieved an impressive 91.2% accuracy on the much broader and generally easier Match 500 benchmark.
Wow. So training on harder problems didn't hurt performance on easier ones. It actually seemed to help overall.
That's the strong suggestion. Exposure to competition-level complex problems appears to enhance generalized reasoning abilities that easily translate back to solving less difficult problems more effectively. It acts as a kind of high-leverage training strategy for reasoning itself.
Train hard, fight easy, basically.
Things like that, yes. It suggests complexity is a good teacher for generalization in this domain.
Okay, now we get to directly addressing factor I of the LIMO hypothesis. The completeness and quality of the pre-trained knowledge base. This, for me, was perhaps the most striking ablation study in the paper because it really isolates the contribution of the foundation model's innate knowledge before LIMO even touches it.
Agreed. This one is incredibly clear-cut. The methodology here was brilliantly simple and ultimately very conclusive. They compared 2 models that had the identical 32 billion parameter count and the same underlying architecture.
So size and architecture are controlled for.
Exactly. But these 2 models had dramatically different pre-training qualities, specifically regarding math and code.
Yeah.
They compared Qwen 1.532b chat, an older generation model, versus Qwen 2.532b instruct. As we noted earlier, Quen 2.5 benefited from significantly enhanced mathematical and code-related content in its massive pre-training corpus.
And crucially, both of these different backbone models were fine-tuned using the identical 800 high-quality LIMO samples.
Identical minimal SFT process, different foundations.
And the resulting performance gap is, well, it's not just wide. You called it an abyss earlier, and that feels right. On the AM 2024 benchmark, the older Quen 1.5 model, even after LIMO fine-tuning, achieved a pretty negligible 9.2% accuracy.
Barely above random guessing for many problems.
In sharp contrast, LIMO built on the better foundation, Quen 2.5, achieved that impressive 63.3% we discussed. That is a staggering 54.1 absolute percentage point difference.
Just from swapping the pre-trained foundation, nothing else changed.
And the same pattern held on the Math 500 benchmark too, right?
Yes, very clearly. Quen 1.5, fine-tuned with LIMO, achieved 65.2% on Math 500, whereas LIMO on Quen 2.5 achieved 95.6%. That's still a massive 30.4 percentage point difference.
The conclusion seems undeniable then. The ability of the model to effectively utilize these minimal, high-quality exemplars, the cognitive templates from LIMO, is overwhelmingly and profoundly dependent on the richness of the pre-trained knowledge foundation.
Absolutely. The templates only work effectively if the fundamental knowledge they are meant to elicit and structure is actually present in the model in the first place. You simply cannot teach advanced meta-reasoning on a brittle or knowledge-poor foundation, no matter how good your templates are. Factor I is non-negotiable.
It really highlights the importance of investing in that base pre-training.
Without a doubt.
Okay, so following that investigation into the quality of the pre-training, the team naturally investigated the more traditional scaling law, the role of parameter count. Does simply making the good quality backbone bigger help?
Right, the standard bigger is better check.
They did this by fine-tuning models from the Quen 2.5 Instruct series, which has that strong math foundation, but at different sizes, ranging from 3 billion parameters up to 72 billion parameters. And crucially, all of these different sizes were fine-tuned using the exact same 800 LIMO samples.
Yep, isolating the effective scale, holding the foundation quality family and the SFT data constant.
Yeah.
Figure 6 in the paper confirms the generalized scaling law does hold here. Performance on the tough AIM E24 benchmark showed steady marked increases with model size.
What were the numbers, roughly?
It started at a minimal 2.5% accuracy for the small 3B model and climbed consistently up to 68.3% for the largest 72B model. This clearly shows that the LIMO fine-tuning approach benefits significantly from increased model scale, assuming the underlying foundation quality is good. Bigger models could leverage the LIMO templates better.
However,
Yeah.
there's always a however in scaling laws. The data also seems to reveal the limits or diminishing returns of pure scaling within this minimal data paradigm, doesn't it?
That's the crucial nuance, yes. While the scaling trend is clear, look at the difference between the 32B model, which, remember, achieved that strong 63.3% on AME24, and the much larger 72B model, which got 68.3%.
That's only a 5 percentage point gain for more than doubling the parameters.
Exactly. That's a critical observation, especially for anyone managing computational resources. It indicates a clear diminishing return curve relative to the parameter count increase, at least for this particular set of complex tasks, and using the specific minimal training data approach.
So the bang for your buck drops off quite sharply at the higher end.
It certainly appears to. The investment required to train, host, and fine-tune a 72B model versus the 32B model is substantial, as you know. Yet the marginal performance gain achieved here using the LIMO methodology suggests there might be a practical saturation point for resource efficiency. The sweet spot of performance-to-cost ratio likely resides well before the absolute maximum model size, maybe around that 32B mark or slightly larger.
Interesting. So scale helps, but maybe not indefinitely or cost-effectively with this approach.
That seems to be the takeaway.
Okay, the final research question, RQ5, brings us back full circle to efficiency. What is the minimum effective data set size for LIMO? And does simply adding more high-quality LIMO data continue to yield proportional returns, or do we hit a wall there too?
Right. This is testing the less is more claim directly on the data quantity axis, but using only high-quality data this time.
To do this, they ranked their entire LIMO pool of 2,125 high-quality problems and solutions, presumably by that quality score we discussed. Then they tested performance by fine-tuning on incrementally larger subsets, starting from just 400 samples, LIMO 400, and going up in steps to 2,000 samples, LIMO 2K.
Exactly, creating a curve of performance versus high-quality data quantity. The analysis of these incremental gains, shown in Figures 7 and 8, is really a masterclass in data efficiency study. The most immediate finding was the absolutely massive initial gain achieved by even the smallest sets.
How big was the jump with just 400?
Fine-tuning with just 400 high-quality samples resulted in a dramatic improvement over the base model. It boosted AME24 accuracy from the baseline 16.5% all the way up to 57.5%.
Wow, that's a 41 percentage point gain with just 400 highly targeted instructions. Incredible leverage.
Phenomenal leverage. It shows how potent good cognitive templates can be, even in tiny quantities, on a strong foundation.
The core finding supporting the less is more aspect specifically comes from the demonstration of early plateau effects, right? Diminishing returns kick in quite quickly.
Very quickly. The performance gain observed when moving from LIMO 800, which got 63.3% on AIM, to LIMO 1K2, adding another 400 high-quality samples, was almost negligible. It was only a plus 0.9 percentage point gain on AME24.
So doubling the high-quality data from 400 to 800 gave a big jump, but doubling it again from 800 to 1600 or adding 400 to get to 1200 yields almost nothing.
Essentially, yes. You're spending significant effort and computation curating those extra samples isn't free to harvest truly marginal returns beyond the initial 800 or so.
And did the performance ever saturate completely?
It came close. While the largest data set they tested, LIMO 2K, 2,000 samples, did yield the highest overall result at 69.6% on AME24, the marginal improvement over the LIMO 1.6K set, 1,600 samples, was tiny, only plus 1.3 percentage points.
So adding the last 400 samples barely moved the needle.
Exactly. This scientifically demonstrates that while slightly more high-quality data is technically better up to a point, the 800 sample set truly represents the sharpest, most efficient peak of the data efficiency curve for achieving highly competitive performance on these difficult benchmarks. For practical, resource-constrained SFT efforts, targeting this minimal, high-leverage threshold around 800 samples seems to be the demonstrably superior strategy compared to chasing those last few diminishing percentage points with much larger data sets.
Find the knee of the curve and stop there.
That's the efficient approach suggested by this data. #tagoutro.
So what does this deep dive into the LIMO paper fundamentally tell us? Wrapping it all up, the core achievement seems undeniable. Competition-level complex mathematical reasoning, which was previously thought to require these vast, massive data scaling efforts,
Hundreds of thousands of examples.
can actually be reliably elicited using a surprisingly small data set, just 800 high-quality examples in their main result, achieving state-of-the-art performance while minimizing data and compute requirements by, potentially, factors of hundreds compared to the old way.
Yeah, the efficiency game is the headline. The LIMO conclusion really serves as a decisive directive, I think, for R&D and investment in the LLM sector. It's an economic argument as much as it is a scientific one.
How so?
Well, those two pillars of the LIMO hypothesis invest in rich pre-training, factor one, and then use minimal, high-quality cognitive templates for fine-tuning. For factor two, they argue this must now dominate the strategy for efficient capability development. First, invest heavily in superior pre-training corpora to establish that robust latent knowledge base. That's the necessary foundation. You can't skimp there.
Factor I is table stakes.
Exactly. Second, focus your post-training SFT efforts exclusively on the meticulous, probably costly, but absolutely essential construction of exceptional demonstrations of cognitive processes. Ensuring those logical steps are explicit, verifiable, and traceable, that's factor two.
So shift resources from massive, low-quality SFT data collection to smaller, extremely high-quality cognitive template creation.
Precisely. Because the data clearly shows that massive resource expenditure on uncurated or even just lower quality large data sets for SFT is not just computationally wasteful.
As shown by the Newman math degradation.
Right. It's proven to be potentially actively detrimental to the model's final reasoning performance. The future for efficient reasoning enhancement seems to lie in surgical precision with data, not brute force scale. Quality, not quantity.
We saw in those ablation studies that the difference in AIM performance between LIMO 800 and LIMO 2K was only about 6.3 percentage points, but required an extra 1,200 meticulously curated samples. That's a lot of effort for a small gain.
Diminishing returns in action.
But even more compelling, perhaps, was the fact that LIMO 400, just 400 samples, already achieved 57.5% accuracy on AIM, representing that incredibly steep initial part of the performance curve.
Huge initial impact.
So, given that LIMO 400 provided such a tremendous initial gain, the challenge we want to leave you, the listener, with is this. How might future research leverage sophisticated techniques? Maybe things like active learning to intelligently select the most impactful samples. Or perhaps reinforcement learning with human feedback focused specifically on verifying the structure and self-correction within reasoning chains. Could we use these methods to achieve that same competitive performance level, maybe that LIMO 800 level or even higher, with potentially even fewer than 400 hyper-optimized, strategically chosen samples?
Could we push that efficiency boundary even further?
Exactly. The frontier of reasoning development has, it seems, definitively shifted from a game of volume to a game of quality and precision.